Hey everyone, and welcome. Today we are going to jump into what I think is one of the most practical and honestly coolest chapters in all of physics, calorimetry. We're going to break down the science of heat, and trust me, by the end of this, you'll see it everywhere, from our weather to the way you cool your drinks. All right, let's get into it. So, picture this. You pour some boiling water into a mug for your tea, and you stick a metal spoon in it. A second later, you go to grab the spoon and, ouch, the handle is already super hot. But the mug, you can still hold it just fine. It's the same hot tea, so what is going on here? That question, that simple everyday experience, is exactly what we're going to figure out today. It's all about how different things handle heat. To make sure we really get this, we've got a super clear roadmap. First up, we'll nail down the absolute basics, the difference between heat and temperature. Then, we'll get into why some materials are just better at holding heat than others. After that, we'll see what happens when hot and cold things mix. And finally, we're going to uncover this amazing idea of hidden heat that lets ice melt and water boil. Sound good? Let's get started. All right, first things first. We use the words heat and temperature pretty much interchangeably, right? It's so hot today, the temperature's high. But in physics, they mean two completely different things. And you know what? Getting this difference right is the key to understanding everything else in calorimetry. So let's lock this in. So, what is heat really? Well, think about anything around you. It's made of trillions and trillions of tiny molecules that are always moving. They're vibrating, they're buzzing around. Heat is the total amount of that internal energy from all those molecules put together. And the big idea here is that it's energy on the move. It's the energy that flows from something hotter to something colder. And since it's energy, we measure it in joules. So then, what's temperature? Well, if heat is the total energy of all the molecules, temperature is the average energy of those molecules. Think of it like this. Temperature is like a signpost on a one-way street. It doesn't tell you how many cars are on the road, but it tells you exactly which way the traffic is flowing. And heat always flows from a higher temperature to a lower temperature, every single time. Its official SI unit is Kelvin, but yeah, we use Celsius all the time. This table here just lays it all out perfectly. Let's run through it. Heat is a form of energy. Temperature just tells you which way that energy is going to flow. Heat is measured in joules, temperature in Kelvin. We measure heat with a method called calorimetry. Temperature, you just need a thermometer. But the last one? That's the absolute game changer. Heat is the sum of all the energy, while temperature is just the average. This means you could have a giant iceberg that has a huge amount of total heat energy, but a very low temperature. And at the same time, a tiny little spark from a fire has a super high temperature, but actually very little total heat energy. Mind-blowing, right? Okay, so now that we've sorted out the whole heat versus temperature thing, let's circle back to our spoon and mug. Why do they behave so differently in the same cup of tea? The answer lies in a property called heat capacity. So let's find out. Who can really handle the heat? First, we have what's called heat capacity. You can think of this as the amount of heat energy, Q, that you need to pump into an entire object, like that whole spoon, to raise its temperature, delta T, by just 1 degree. So this value depends on two things: what the object is made of and how big it is. A huge wooden log is going to have a way higher heat capacity than a tiny little splinter of the same wood. But what if we want to compare the materials themselves without having to worry about the size or shape of the object? Well, that's where specific heat capacity comes in, and we use a lowercase c for this one. This is a property of the substance itself. It tells us how much heat it takes to raise the temperature of exactly 1 kilogram of a substance by 1 degree. This lets us compare apples to apples, or, 1 kilogram of copper to 1 kilogram of water. It's like a unique fingerprint for every single material. And this table just sums it all up perfectly. Heat capacity, the big C, is about the whole object, which is why its mass is part of the deal. But specific heat capacity, the small c, is about the substance itself. It's a fundamental property, just like its color or density. And you can spot the difference right in the units. One has per kilogram, the other doesn't. That per kilogram is the giveaway that we're talking about the material's basic ability to soak up heat. Now this is where it gets really, really interesting. Just look at these numbers. Lead has a super low specific heat capacity, only 130. That means it heats up and cools down really fast. Copper and iron are a little higher, but then look at water. Its value is 4,200, 4,200. That is absolutely enormous. It's more than 10 times higher than copper. And that isn't just a random number. This is a genuine superpower that affects our entire planet. So why is this superpower such a big deal?
Well, because water can soak up a massive amount of heat without its own temperature changing very much, it acts like a giant thermostat for the Earth. If you live near the coast, you've felt this. The land heats up fast during the day, while the ocean stays cool, giving you that nice sea breeze. At night, the land cools down quick, but the ocean slowly releases all the heat it stored up, giving you a warm land breeze. It's also why water is the perfect coolant for car engines. It can carry away tons of heat. It's why a hot water bottle stays warm for hours. Farmers even spray their crops with water on cold nights. As that water cools down, it releases a lot of heat, which protects the plants from frost. It's absolutely amazing stuff. Okay, we've seen how different materials absorb heat, but what happens when we actually mix them? Like what happens when you drop a hot piece of metal into some cold water? Where does all that energy go? Well, this is where we become heat detectives, and we use something called the principle of mixtures to follow the trail of energy. This right here is the golden rule, and it's really just about the conservation of energy. If you have a closed-off system, meaning no heat can escape, then the heat that is lost by the hot object is exactly equal to the heat gained by the cold object. The energy doesn't just disappear, it's just transferred from one to the other until they both settle at the exact same final temperature. And we call that final state thermal equilibrium. So how do we actually measure this heat exchange in the lab? We use this device called a calorimeter. It's actually a pretty clever design to keep it a closed system. The inner part is a copper cup, and we use copper because it's a great conductor, so heat spreads through the water quickly and evenly. But then that cup is surrounded by insulation, like cotton wool, and placed inside a wooden box to stop any heat from escaping out into the world. It's basically a fancy thermos that we use for our physics experiments. And this brings us to the mathematical heart of the chapter. Heat lost equals heat gained. Now, don't let the formula intimidate you. Let's just break it down. On the left side, we have M1, C1, and T1. That's the mass, specific heat, and starting temperature of the hot thing. On the other side, M2, C2, and T2 are the exact same things for the cold thing. And that lonely letter T in the middle, that's the final temperature that they both settle at. So the left side is just the heat lost, and the right side is the heat gained. Simple as that. All right, now for something that feels a little like a magic trick. Imagine you've got a beaker of water on a stove with a thermometer in it. You crank up the heat, the temperature starts climbing, 80 degrees, 90, 95, it hits 100 degrees Celsius and starts boiling away. But here's the mystery. You keep the flame going, but the thermometer, it just stays stuck at 100 degrees. It won't go any higher. So where is all that extra heat energy going if it's not making the water hotter? The answer is something called latent heat. And the word latent literally means hidden. This is the hidden energy that's being used not to make the molecules jiggle around faster, but to actually break the bonds that hold them together as a liquid. It's the energy required to change the state of something, like from a solid to a liquid or a liquid to a gas, and it all happens at a constant temperature. The formula is pretty simple. Latent heat, L, is just the amount of heat, Q, you need per kilogram, M, to make that change happen. This graph of ice being heated shows it perfectly. Take a look at the first part, segment AB. We're adding heat, and the temperature of the solid ice is rising from below 0 up to 0 degrees Celsius. Simple enough. But then look what happens at point B. The temperature hits 0 and it just flatlines all the way across segment BC. We're still pumping heat into it, but the temperature does not change. Not one bit. All of that energy is being used as latent heat of fusion to break apart the ice crystals and turn solid ice into liquid water. It's only when all the ice has melted at point C that the temperature of the water can start to rise again. And guess what? We see the exact same thing when water boils. In segment AB, we're heating the liquid water, and its temperature climbs steadily towards 100. Then at point B, it hits the boiling point. And again, look at segment BC. The water is boiling like crazy, turning into steam, but the temperature is locked at a constant 100 degrees Celsius. All that energy you're adding is now the latent heat of vaporization, giving the water molecules enough of a kick to escape the liquid entirely and become a gas. It's a huge amount of hidden energy. Now, this whole idea of hidden heat isn't just some weird thing that happens in a lab. Just like specific heat, latent heat has massive, real-world effects. You could even call it nature's secret weapon for moving energy around and keeping temperatures stable. Let's see how. Okay, let's connect this to what we see every day. Ever wonder why all the snow on the mountains doesn't just vanish the second the temperature gets above 0? It's because of ice's huge latent heat of fusion. It takes a massive amount of energy from the sun to melt all that snow, so it happens slowly, which prevents crazy floods.
Or here's a good one. Why is ice at 0 degrees so much better at cooling your drink than the same amount of water at 0 degrees? Well, as that ice melts, it has to suck a ton of latent heat out of your drink to do it, which makes your drink much colder, much faster. It's the same reason lakes don't freeze solid in a single night. And have you ever noticed how it feels extra, extra cold right after a hailstorm? That's the hail on the ground absorbing latent heat from the air and from you so it can melt. Okay, let's put this all together. Say you have a problem that asks for the total heat needed to turn 1 kilogram of ice at minus 10 degrees Celsius into water at 100 degrees. You can't just do it in one step. You have to break it down. Step 1, you heat the ice from minus 10 up to 0. For that, we use Q equals mc delta T. That's 1 kilogram times the specific heat of ice, which is 2100, times a 10-degree change. That gives us 21,000 joules. Step 2, we have to melt that ice at 0 degrees. Here, we use the latent heat formula, Q equals L. That's 1 kilogram times the latent heat of fusion for water, a whopping 336,000 joules. Step 3, now we have water at 0, and we need to heat it all the way up to 100. It's back to Q equals mc delta T, but we use the specific heat of water this time, 4200. So that's 1 times 4200 times 100, which is 420,000 joules. For the final answer, you just add up the heat from all 3 steps. See? When you break it down, it's totally manageable. So, we have covered a ton of ground today. We've seen that heat is energy in motion, and temperature is its guide. We've learned that water's incredibly high specific heat capacity makes it a global thermostat, and its high latent heat acts as a powerful buffer against sudden, drastic temperature changes. So I'll leave you with this one last thing to think about. If water had a really, really low latent heat of fusion, what do you think would happen to our planet every single spring? Think about it. Thanks so much for joining this explainer. Keep practicing these concepts, stay curious, and you will absolutely nail this chapter.